Okay, today's video is over AROC versus IROC, which, as you can probably assume from the acronym, stands for average rate of change and instantaneous rate of change, respectively. Now, I should mention that AROC and IROC are important concepts, but IROC is seen much less frequently in calculus, although it is important as FRQ questions on exams will occasionally show up featuring AROC. So at this point, I'm going to go over what AROC and IROC are. AROC is the rate of change of a slope or a rate of change of a curve with respect to its independent variable over 2 points, so over an interval, and it can be modeled as y of f minus y of I over x of f minus x of I. And as you can, if you'll recall from your 6th or 7th grade class, can also be modeled as slope, and that's a fine way of thinking of it. I would like to note that when I say change of x or change of y with respect to x, I'm really saying as x changes, how does y change? And that is what or a derivative is really. The second topic we'll go over is IROC, which is the instantaneous rate of change, the change at a certain point, 1 point. And this is a bit of a more abstract concept. And it can be found using a derivative. And a derivative is just, a way to find the slope at a certain point. Now, I believe AROC and IROC are both featured at near the beginning of Calculus AB, and so you may be unfamiliar with derivatives, but that's okay, because you'll learn processes over how to find derivatives and whatnot. It can be modeled as dy dx at a certain point, x equals whatever. It can also be modeled as f prime of something. I'm just going to call it c. The point at which we're trying to find at the point at which we're trying to find the instantaneous slope. It can be also modeled as d dx with respect to c. This means that we are taking the derivative with respect to x at the point c. That's what these all mean over here on the IROC section, meaning like how f of x changes as x changes. That's a great way to think about it. Now with AROC, the average rate of change, the change from 2 points, x initial I, y initial I, and x final I, x y final I. You'll see occasionally on FRQ questions, mostly in Calculus AB, you'll usually be given a table of x and y coordinates, or any independent coordinates and any dependent coordinates. And you'll be told to find the average rate of change at a certain point. And as I said, you'll probably come across one question in the entire AP exam featuring AROC. In order to find it, you just take the y at a point minus the y at another point over x at a point minus x at another point. And so long as the point at which you're trying to solve it is found in this interval, then you can take the AROC. So for instance, if I were to give you a table, I'm just making up on the spot. Actually, okay, that's fine. And it looked a bit like this. Actually, let me change these values a bit. Looked a bit like this. And you were asked to find the value of, let's say, the average rate of change at x equals 7. Well, you could take the interval from 9 to 5 if you so wished, or you could take the interval from 9 to 7, or the interval from 7 to 5. Since these all feature the point at which you're trying to find the instantaneous rate of change, that point being 7. AROC is just so infamously inaccurate that it really doesn't matter the point at which you're trying to solve it. And that's the reason why it's very rarely seen in Calculus AB or VC, because calculus is really just the analysis of a curve using a limit. And since AROC doesn't feature a limit, it's not very often seen. Okay, this is practice problem 1. In this practice problem, we're going to employ AROC. Now, I don't know if any of the data in this question is correct. I just made it up. But this is what a typical AP FRQ will look like, one that features AROC. So we're not really given much space. but I'll try to make do. So we're told that a study found that as the pressure of atmosphere increased, so did the temperature. With the data provided, find the average rate of change at which the temperature changes at a PSI of 15. So, 1 second. Okay. So we're given our dependent values, we're given our independent values. As these change. So that means that we can model this as y, we can model this as x, and a derivative, which we're not going to go over yet, since this is AROC, will just be dy dx. But I suppose we should go over it. So we're average rate of change at PSI of 15. That means our interval at which we have to find it has to include 15 at one point. And the only one that will allow that would be the interval from 16 to 17. I suppose we could do 19 to 13, 16 to 10, 19 to 10, but this is the most accurate, and so we're going to stick with this. So the interval we're going to use is going to be 13, 16. These are the x values that we're going to take the average rate of change at. So we'll model that as f prime of 15. And we can say that that's approximately equal to the average rate of change of f of 16 over 13. Sorry, f of 16 minus f of 13 over 16 minus 13. And this is, of course, equal to 83 minus 65 over 3, which is equal to 18 over 3, which is equal to 3. And so you responded to this type of question with a written response rather than a mathematical. You'd say that at a PSI of 15, the temperature is increasing at approximately 3 degrees Fahrenheit. And so that is a typical FRQ question featuring AROC. Okay, this is practice problem 2. This it expands upon the last one. That you'll see similar things in AP exams, where sequential problems will elaborate on the last one. But anyways, we're told that a more accurate model of the relationship between pressure and temperature is developed, and it can be modeled as f of x is equal to natural log 2x. Find f prime of 15. Now, this data has nothing. This model is totally made up. I just came up with it off the top of my head, and all the data, if there is any relationship, is totally accidental. Anyways, we got to find f of 15. When you're asked to find the rate of change, always assume that it's instantaneous or just the derivative of something, because AROC, as I said, is very uncommon, and you'll be explicitly stated to use AROC if it calls for it. So we're going to find f of 15, which is just the derivative of f of x at point 15, at point x equals 15. So we're going to start off by finding f prime of x, the derivative of f of x, also known as just the slope of f of x at any given point. So natural log 2x, it's been quite some time since I've taken calculus AB. I'm not sure at which point AROC versus IROC is introduced. So you may be familiar with the derivative of natural log. It's fine if you're not. I'll go over it now. So if we were to take the derivative with respect to x of natural log x, or rather a natural log f of x being the argument, we can equate this to f prime of x over f of x. And so that's just the simple formula for derivative of natural log f of x. In this case, f of x is 2x. So we need to take the derivative of natural log 2x. The denominator is just going to be the argument, which is 2x. The numerator is the derivative of the argument, which is going to be 2. Meaning that our derivative of f of x is 1 over x. And so now we have to find f prime of 15. This is equal to, you guessed it, 1 over 15. Now this is not at all close to the value of the last question, or the value found in the last question, and that's fine, because not all of the equations in calculus are practical or reasonable or logical. But anyways, using this more accurate model, we found that the instantaneous rate of change of the relationship between pressure and temperature at point or at the PSI of 15 is 1/15. That's actually it for today's video. If you have any suggestions, please put them in the comments below. Thank you.